Hi, I'm Jonathan from Google DeepMind. Today I will be talking about signal loss. Calibration is critical for the online performance of our recommender systems. But our ability to calibrate is actually hurt by the loss of event level labels. Today I will be talking about how we address this problem in streaming recommender systems at Google. We all know that user feedback is the fuel of our recommender systems. We have a set of users and a set of items, and we have logged feedback from these users, and we use it to train our recommender models. But what if we lose this fuel? And this is actually happening under tighter data controls. We have a signal loss problem. And in this scenario, our models are becoming biased, so they are over or under predicting, which respectively results in over or under spending, and they are also becoming inaccurate. So can we recover the performance of our models under these circumstances? Fortunately, not all is lost. We still have a signal. It is just much weaker. So instead of having different user feedback for each item, now our feedback is going to be aggregated across users. And as a result, we're going to have item-level aggregates instead of event-level labels. The question that we want to address is, how can we use these aggregates to learn from them and train our recommender models? And specifically, how can we do this when our recommender model is training in a streaming fashion, where samples arrive chronologically and we keep training our model? In terms of learning from the aggregates, we can leverage a field called learning from label proportions, or LLP. And this is a weakly supervised setting. In this scenario, our training samples are going to come in the form of groups that we call bags, and the labels are going to be aggregated across these bags. So instead of having our traditional pointwise labels, we're just going to have information about the distribution of classes within each of these bags. And our goal is going to be to learn an instance level classifier based on these aggregates. A very common framework to learn from these proportions is to use what we call an aggregate loss. And this is a bag level measure of discrepancy between the model's predictions and the actual labels. And concretely, if we take a bag and it has a set of items, we can perform inference with our model on each of these training examples. We can then pull these predictions, and we can compare this with the label proportions with our aggregate loss, and then we can backpropagate to our instance level predictions from our model. However, we can see that this has two assumptions. One is we need clearly defined bags that allow us to compute an aggregate loss, and in addition, we need each sample to be present, each sample from each bag must be present in the same batch at the same time for us to be able to backpropagate properly. And we call this bag-batch alignment. Unfortunately, in the streaming setting we were talking about, these assumptions are not really met. In terms of having clearly defined bags, we receive noisy conversion reports for the user feedback, so it is non-trivial to slice by time in the presence of this noise. We can form our bags by looking at items, but we don't know when to slice by time. And then in terms of bag-batch alignment, a lot of these systems are designed to deal with such large amount of data that we incur the infrastructure batching constraints that don't allow us to have fine control over the composition of the batches. In addition, some bags are going to be so large that they don't really fit in a single batch. So this introduces a bag-batch misalignment problem, which means we can't backpropagate properly in the way we were talking about before. How do we then apply LLP in this scenario? The key insight here is we can design a pointwise loss that has a gradient that behaves in a similar way to the gradient of the aggregate loss. If we look at the L2 loss, when we perform our pointwise approximation, we obtain a loss that looks like this. And it has the model predictions, and they are multiplied by some weights. And these weights correspond to the mean error of the model on the corresponding bag. we can estimate these weights based on the past samples using moving averages. And that means that if the mean error is positive, meaning the model has been over-predicting on this bag or this item, then the predictions are going to be pushed down. And if the mean error is negative, meaning the model has been under-predicting, the predictions are going to be pushed up. And conversely, once the mean error has reached 0, indicating good calibration, we can expect no change. So this has a calibrating effect. We can apply our same approach to other losses. For example, the cross-entropy loss. And when we apply our approximation, we obtain a similar pointwise loss as in the L2 case. We still have the mean error as the weights, except now instead of the predictions that we had in the L2 case, we now have the model logics. And this has a similar calibrating effect. With this approximation, we can build our approach, which we called cross-batch aggregate loss, or XBA, and it will allow us to do LLP for streaming. The first component is going to help us define the bags in spite of this fuzzy time alignment issue. And to address that, we're going to use moving averages. This is going to act like a moving window, and our estimates are going to converge to the true values. So as we consume more and more batches, we update these estimates of the mean label and the model's mean prediction for each of the bags. Now that we have these estimates, we can apply our aggregated loss pointwise approximation, and this is going to help us address the back-batch misalignment problem. So once we receive a new element from a bag, we can use our existing mean label and mean prediction estimates and apply our XBA pointwise approximation of the aggregate loss for this sample. And this allows us to backpropagate properly. In this way, each sample is aggregated with the past across batches using a moving window. Now that we have this loss, we need an architecture to learn using this loss. And specifically, we look at the scenario when we receive a mix of pointwise labels and aggregate-level labels. So for the pointwise labels, we have a dedicated tower that we call the event-level training tower, or ELT. And then using components from it, we build the aggregate-level training tower, or ALT, that we train using XBA. And the design is motivated by the fact that because XBA is an aggregate loss, it's going to be much looser where compared to a pointwise loss. So it's going to be under-constrained, and this is going to entail a risk of overfitting. And the way we mitigate these risks is we reuse some of the ELT components, specifically the embedding and the logic, and we protect them with a stop gradient. We also ensemble 2 of these towers, and we apply L2 regularization. In addition, we use cold start item bias as a proxy for overfitting. We implemented this in a Google ad streaming model, given these results. First, we see better offline bias. In addition, we see accuracy improvements, indicating that we have successfully learned from the aggregates. And when we go online, we see a better distribution of the online bias, and this delivers better value to advertisers. In addition, we also observed better cold start calibration. As a result, we launched this model, and it delivered improvements in key business metrics and advertiser value. Our technique adapts LP research to industrial recommenders that are impacted by signal loss, and we do this through a loss design with a pointwise loss that has a gradient that mimics the aggregate loss gradient. We also use moving averages, and these converge to the true means, and they adapt to the time dynamics. And this delivers key online and business metrics improvements. Thank you for your time. I'm happy to answer any questions, and please come to our poster on spot 29.
So, for example, how does cross-batch aggregation cope with concept drift in streaming data?
Yeah, I think one of the challenges in the streaming setting is that our data distribution is changing. This is why our moving averages that we're using, they use decay, so they're going to adapt to the time dynamics, and they're going to focus on the most recent samples.